Hi everyone. I would like to talk a little bit about Taylor series. So I'm going to do an example here where I'm looking at the function cosine and I'm going to come up with an approximation around pi over 2. And the first step for doing this would be to make a table. And in the first column, I'm going to put all my derivatives. And you can take this out as far as you want to. I only did it up through the third derivative. So for example, the function itself is cosine, and then the first derivative would be negative sine, and so forth. In the second column, I'm going to evaluate my function or my derivative at my point pi over 2. So for example, f of x evaluated at pi over 2, I'm just going to substitute that in. So I'm looking at cosine of pi over 2, and that would be 0. On the next line, I've got the derivative. First derivative here is equal to negative sine of x. And if we want to evaluate that first derivative at pi over 2, I'm substituting that value in. I'm looking at negative sine of pi over 2, and that would be a negative 1. And I keep on going. So those numbers I get, those little coefficients, those are going to feed into the Taylor series formula. And it looks big and scary, and there is a lot to it. And certainly there's a lot of beautiful mathematics behind it in terms of deriving it. But we're just plugging in values. So all we have to do is kind of follow the recipe here, and we don't have to really get too tangled up with anything else at this point. So when you look at this formula, I want you to notice patterns. So the denominators are all factorials, and they start at 0 factorial, which is just 1, and they march right on up. Now, the next piece I'd like you to look at is the numerator. And notice that we have x minus c to the 0th power, x minus c to the 1, x minus c to the 2, etc. So again, there's these beautiful patterns here. And once you see the patterns, it makes it a lot easier to work with. But the only thing we need to work with at this particular point is f of c. In other words, the function evaluated at my point pi over 2. And then next, the first derivative evaluated at pi over 2, and the second derivative evaluated at pi over 2, etc. So that's why doing the table right up in the beginning helps you just fill in these little constants, and then everything else is copy-paste. So for example, for our function, that first constant is just going to be a 0. So that wipes out that first term entirely. And then the next constant we found was a negative 1, so I'll put that in, and then x minus pi over 2 to the first power. And you keep on going, just plugging in your constants. So nothing too bad so far. And then if you want to look at your first Taylor polynomial, I'm going to call it T1. You're looking up through the linear term here, and so that would just be 0. I can ignore that. Negative parenthesis x minus pi over 2. And then you can keep on going. Notice my second Taylor polynomial, my quadratic term was 0, so that wasn't very exciting, but you can keep on going. Now let's take a look at a plot. Okay, so I'm over here in Desmos, and I've plotted my cosine function. The next thing I'm going to do is I'm going to plot my point pi over 2. So when x is pi over 2, I'm looking at the point pi over 2 comma 0. So basically, I'm looking for an approximation around this point. And I've got a huge section of this cosine curve. I don't need that in my life right now. So I'm just going to adjust the viewing window here to maybe go, negative 1 up to, 5 or something. Seems a little bit better. And then maybe on the y-axis, negative 5 to 5. That looks better. I can see kind of a closer view of what I'm working on, and I still see the axes here. All right, so now let's do our first Taylor polynomial. Okay, so I've typed in our first Taylor polynomial, and that does a pretty good job, pretty good approximation. Now, obviously, if I'm way over here at like x equals 4, there's going to be a lot of disagreement or a lot of error between my true curve and my approximation. But as I'm snuggled up close to pi over 2, my approximation does a really good job. Okay, now T2 was the exact same expression, so I won't bother with that, but I will look at T3. And I've got a lot of red curves on here, so let's go in and maybe edit some of these. I'm going to make my original function a nice black curve, and I'm going to make it a very bold line. And then I've got these other ones on here, which look fine. So that's pretty interesting. I mean, you can zoom in here even a little bit more if you wanted to. So my original function is the bold black curve, and then just doing the third degree Taylor polynomial there, that red one, wow, there's a lot of agreement, even when I'm pretty far away from my point of interest. I mean, even when I was over here at 0, that approximation is looking pretty good. And obviously, if I used a weaker approximation, I certainly see more error there with that purple curve. But this is the idea. And then you can go in here and you can share your graph. You could either choose to embed it, which is kind of nice. I'll copy paste this. I'll go back over here. And in Canvas, you can click on the HTML and just paste. And then the graph shows up right there. The other thing you could do is certainly export the image as a JPEG and share that. You can also just copy the URL in case anyone else wanted to play with the graph, and then it's linkable. So that's a really nice way to share your work.